Hi everyone, I'm Ian Smith from MIPI Alliance, and I'd like to welcome you to today's webinar. I'll be your moderator for today. So today we'll be hearing about JEDEC UFS, MIPI UniPro and MIPI M-PHY, winning combination enabling state-of-the-art flash storage solutions. We've most certainly got the experts in the house today to talk about these areas of interest. Three speakers for you today. Firstly, we have Sergio Silva, Program Engineering Manager from Synopsys and Chair of the MIPI M-PHY Working Group. We have Ramesh Hanchanal, ASIC Digital Design Manager from Synopsys and Chair of the UniPro Working Group. And Bruno Trematore, Chief Engineer at Kioxia and Co-Chair of the JEDEC UFS Technical Group. So that said, let's have a little look at our agenda for today. I'll give a very quick introduction to the today's webinar and the specifications we'll be talking about. And I will then hand over to Sergio to talk about MIPI M-PHY v5.0, then Ramesh to talk about UniPro 2.0, and then Bruno will talk about JEDEC UFS 4.0. So with that, let's get started. I'll quickly run through my introduction. I'll make this as quick as possible. So firstly, you'll note today that the webinar has been brought to you by both JEDEC and MIPI Alliance. JEDEC MIPI Alliance are two standard-setting member-led industry associations working in the electronics industry. You can see here the mission statements for both organizations. JEDEC's being to serve the solid-state industry by creating, publishing, and promoting global acceptance of standards and providing a forum for technical exchange of topics of industry interest. And the MIPI Alliance mission to provide the hardware and software interface specifications that device vendors need to create state-of-the-art, innovative, mobile connected devices whilst accelerating time to market and reducing costs. So those are our two host organizations for today. The reason we have two organizations is that we're both liaising in various aspects. In fact, since 2008, JEDEC and MIPI have had a long, productive history of industry liaison. Two key highlights to mention today. Firstly, the JEDEC MIPI MOU that has enabled UFS to leverage MIPI M-PHY and UniPro to create a flash storage solution for the mobile industry and beyond. And that's what we'll be talking about today. But also in addition to this, and more recently, JEDEC and MIPI liaison agreement has been signed to allow use of MIPI I3C for JEDEC sideband bus in DDR5 solutions. To just give a little bit of a introduction as to why we're talking about three technical specifications today. Well, together they form a storage solution, the UFS storage solution, which is based upon the UFS 4.0 technical specification from JEDEC plus UniPro v2 and M-PHY v5. The UFS uses UniPro as its link layer and M-PHY as its physical layer. And today they provide this leading storage interface that's enabled in many 5G-enabled smartphones today, and also a growing number of automotive applications. Today we'll hear about current specifications, but obviously technical specifications by the nature constantly evolve. And we'll touch on what's happening in the future with M-PHY v6, which offers further bandwidth increases, and also UniPro v3. And I think this is my last introductory slide. Just to talk a little bit about market adoption. You can see here, and we have some figures that have been provided by Kioxia. You can see that over recent years, UFS has grown to become the dominant flash storage solution in mobile applications. But more interestingly, UFS is also growing rapidly in the automotive sector. You can see that UFS is quickly becoming the dominant flash storage solution also in automotive infotainment areas. Why is that? Well, obviously, this combination of specifications provide fast interfaces, high performance, they're power efficient, supporting ever larger storage capacities with high reliability. So provides an excellent solution for both mobile and beyond mobile applications such as automotive. And in the automotive segment, you can see the areas listed here that that require flash storage solutions. So you're finding it being used in telematics, V2X, ADAS, navigation, infotainment solutions. Okay, well, that's my very quick introduction. It's now time to hand over to our first expert for today. I'd like to ask Sergio to join the stage and introduce us to MIPI M-PHY v5.0. So just give a second for Sergio to rejoin the stage. Here he comes.
Hello, everybody.
Hi, Sergio. Welcome. Right, hand the floor to you.
Okay, thank you. So let's talk a little bit about M-PHY. So what is M-PHY? It's a versatile PHY specification that is meant to be used in mobile applications where performance and power efficiency are paramount. It is the base physical layer for JEDEC UFS 2.0, 3.0, 4.0, and the forthcoming 5.0 specifications. It is indeed currently mainly used for flash memory storage, but it can also be used in chip-to-chip communication applications. It is expected to be the de facto mobile storage interface deployed in 5G-enabled smartphones, but has also found applications in mobile-influenced ecosystems and automotive applications, as we just heard about. So it's a standard that it's tailored for mobile systems, fulfilling the key requirements of low power, low pin count, and low electromagnetic interference. It meets today's devices' high bandwidth and scalability requirements, with performances up to 23 gigabits per lane. It is very scalable, allowing multiple lane configurations and both symmetric and asymmetric link operation. It is well suited for intermittent nature of mobile interchip communication, allowing for quick enter and exit of low power states for both between data transmission and shallow power saving states and deep power saving states such as ironate. M-PHY evolved to improve communication speed, but also latency. It addresses increasing data rate requirements and provides engineers with design flexibility for advanced applications by going up to 23 gigabits per second per lane, as previously mentioned. But it also adapts itself to the ecosystem requirements to remove the need to support unterminated mode and long channels, which are of no real use case in the mobile systems. It implemented the optional reset mode, high-speed mode, which allows for the use of high-speed gear 1, which is around 1 gigabit per second, instead of low-speed gear 1, which is around 9 megabits per second, during boot-up activities, considering lowering the overall device startup time. It also reduced the reset timing sequence by around 10 times. Another feature that was added to the specification was the eye monitor. So eye monitor enables live in-the-field input signal metrics to debug possible faults caused by signal integrity without the need of using external measurement equipment. This reduces debug time and greatly enhances the test and the debug features of the devices using this specification. In summary, M-PHY is a mobile-friendly physical interface which ticks all the requirement boxes, such as scalability, low MI, low pin count, and low power consumption. Above all, M-PHY provides the serial link speed and power efficiency necessary for the increasing data volume of mobile and mobile-influenced applications. I think I can turn now to Ramesh to go through the UniPro slides.
We'll hand over to you to take us through UniPro v2.0. Thank you.
Sure. Hello, everyone. So this is Ramesh, managing UniPro specification body. And today we will talk about UniPro. Jan, can you help me with the slides being moved? Okay, thank you. Yeah, so what is UniPro? Basically, the UFS storage solution makes use of UniPro along with M-PHY to meet its requirements, such as, basically UniPro provides services like transport layer, link layer, and physical adapter. Not physical layer, but yeah, physical layer adapter solutions to the UFS layer. And this also means UFS completely offloads the responsibility of link establishment, link reliability, and link speed control operations to UniPro, which manages establishing these features between host and device of UFS. So in case of UFS 4.0, it is UniPro 2.0 along with M-PHY that will be used to meet the storage solution. After knowing the role of UniPro, we can now double click on UniPro 2.0 major takeaways. That is what the industry currently that is experiencing or seeing the new specifications. So UniPro 2.0 majorly addresses the boot time reduction by introducing link up in high speed. So we will see more details subsequently. And it also introduces the payload size increase, which is going to help improving the performance. So Jan, we can stay in the previous slide, please. Yeah, thanks. So, and yet another thing that, as we heard, physical layer is introducing 23.3 Gbps by having gear 5 operation, so that UniPro takes advantage of that and make sure that the gear 5 is being adapted, and thereby per lane, per direction, 23.3 Gbps is going to be established, which we will see effectively what it means when UFS host and device are going to communicate in the new speed or gear 5 speed. Right. So here, just a block diagram as it shows, UFS solution comprises of 3 major specifications to establish chip-to-chip communication. UFS layer has UIC layer, which manages link layer and physical layer connectivity. Link layer and physical layer are nothing but MIPI standards. Those are UniPro and M-PHY. So in total, we see that 3 protocols addressing the need of chip-to-chip communication in storage. Next slide, please. So, as I said, one of the area that UniPro 2.0 addressing is to reduce or optimize the boot time. Before we understand where it introduced the optimization, let us have a look at what was today's solution or so far solution in the UFS for boot up operation. Boot up used to happen in low speed which is nothing but PWM link-up process. As you could see in the figure, if the application or the upper layer initiates the link startup, which is shown as request time at X, whichever that could be, like, after power on reset, it could be 0 time, or it could be with a little delay, whatever that it would be. If we consider that as a start time, the boot up time or the link up time used to comprise of various components, such as T-activate time, which requires the physical layer to be ready for the operation. Then there used to be a line reset, followed by training operations called as trigger patterns. So the responsibility of these trigger patterns was basically to identify, is there really a remote partner available or the link partner available? And if it is available, with how many lanes? And after knowing the number of lanes, it used to also exchange the physical layer capabilities between the link partners, so that when they go in mission mode, these capabilities can be utilized. So mainly, if we try to abstract it, it used to have line reset followed by trigger pattern exchanges, and it used to involve capability exchanges. All these components, if we sum up, it comes to 9.5 millisecond, but yeah, including the latency or the lead lag situation between the link partners, it goes 10.5 millisecond. Okay, so if there is a need of additional line reset, again, the reason being lead lag situation, then somewhere between 10.5 millisecond to 14 millisecond is what it used to take in earlier solutions. But newer generation UFS solutions needs faster boot up time, so that boot up time shouldn't be a bottleneck, and Zoom it can go into the operation. So, Ian, can we go to the next slide? UniPro is taking advantage of high speed, which is NRZ mode. The link-up operation is now introduced in UniPro 2.0, the link-up operation to be performed in high-speed gear 1, which can be in rate A or rate B, because M-PHY allows to use 2 series, and there can be default, it is going to be rate A, but the picture is trying to show the higher one, which is 1.5 Gbps operation. So components for the link-up remained the same. However, there are optimizations that are introduced. Basically, the T-activate time is being reduced from milliseconds to microseconds. So that has optimized from 1.6 millisecond to 400 microseconds. Line reset period is drastically reduced, which used to range from 3.1 millisecond to 5 millisecond. Now that is brought down into hundreds of microsecond, which is 310, as we see in the figure. And the trigger pattern itself, unlike earlier, where it used to operate in PWM gear 1, which used to range anywhere between 3 Mbps to 9 Mbps, that will suddenly start operating in 1.5 Gbps range. That means HS gear 1, which will bring it down. The trigger pattern will come down to in the range of tens of microsecond. As we see there, it is going to be 41 microsecond, ranging up to 47 microsecond. So all these time reductions will contribute overall time saving. So it brings down to 2 millisecond for link up. So we could see that the boot up time is being reduced anywhere between 8.5 millisecond to 12 millisecond. So that is one of the primary gain what we will have when we move to UFS 4.0 solution. Jan, we can go to the next slide. After knowing the boot time reduction, another major takeaway from UniPro 2.0, which is UFS 4.0, UniPro has introduced increased payload size. Earlier, it used to be 272. Now, the payload size is increased to 1144 bytes. So, even with this increased payload size, the CRC computation engine remains the same because it is known that its protection mechanism remains the same or is suitable even with the increased payload size. So there is no change in the CRC scheme. However, the advantage yet another advantage being, apart from CRC, the overhead or the per packet number of bytes that will be contributed from the UniPro still remains the same, which is 8 bytes. So as second bullet reads out, the UniPro overhead per packet remains same between previous version and the current version, that is 1.8 and 2.0. It is 8 byte itself. Okay. However, 272 byte payload is also retained, so that in the specification we call it as credit mode 32 and credit mode 128. Both the schemes are there, but with the newer payload size, we have much gain in terms of performance. So as we could see there in the figure on the right hand side, in 1 second, the number of packets that can be exchanged, the actual payloads, the bytes that can get exchanged is much higher in a newer version as compared to earlier, right? So in earlier version, for 1 second, we used to transmit roughly around 8,606 packets. That also means the overhead contribution could be 68,846 bytes of overhead. Whereas with increased payload, we will be transmitting 2091 packets. Okay, that means less number of packets, more actual bytes are getting exchanged. That also means reduction in overhead, and now the overhead is going to be 16,733 bytes. So the number of bytes, total bytes reduction for 1 second will be 52,113 bytes, 52K bytes reduction. So this contributes around somewhere 75% of the gain, 75% overhead reduction. Sorry, not gain, 75% overhead reduction as a relative between 1.8 and 2.0 with a newer payload size. That is yet another major gain in UFS 4.0 will be seen. Next slide, please. As we all know that M-PHY 5.0 has introduced gear PHY. The last red line that what we see in the picture is per lane, per direction. That's the M-PHY gear PHY solution that what it offers. In case of two-lane connection, in one direction that contributes to 46.6 Gbps, whereas if we consider full duplex operation, which means 4-lane, 2 on TX side and 2 on RX side, it comprises of 93.2 Gbps. As we see pictorially, for every version, one of the major contribution that is happening by the PHY is doubling the bandwidth, which is again further used by UniPro to make sure in two-lane solution it gives high performance. With the high performance, the UFS solution can improve its memory read-write operations with a higher performance, and it also gives advantage to have better performance for async queuing. Okay, advanced async queuing that is getting introduced in the UFS, they can take advantage of these abilities of UniPro along with M-PHY. So we know that when higher the bandwidth, multiple applications can try to use the bandwidth in time multiplexed manner or in an async manner. So that's where the gain comes out of this feature. Next slide, please. So this summarizes on the left-hand side major changes, but all these major changes also comprises of various nitty-gritties beneath. So the first line covers the physical layer change, adapting gear phi, which is going to be like 23.3 Gbps per direction per lane. So along with that, the phi test mode is also of the UniPro is also updated, and gear phi's adapt mechanism is also utilized or introduced, and power mode change procedure is also updated to support gear phi. So these are the details of UniPro physical adapter layer changes. In link layer side, as I said, the new payload size is being introduced, which means new credit mode. The feature is known with the credit mode as 128, along with the existing credit mode is also retained. And link up in high speed is introduced, just that the link startup procedure need to be selected statically. Either it will be low speed or it will be high speed, and that decision need to be made statically, and then it should use or it should make use of that mechanism of link up. Apart from adding new features, there is certain optimizations that are done to ease the implementation, especially the unused features such as PWM gates from G2 to G7 are removed from the specification. Only the gear 1 is retained. And this also makes a path for future enhancement where we can completely, in the next version, we can get rid of PWM mode completely. So these are the major and a minor details of the UniPro 2.0, which we will see in UFS 4.0. And with that, the walkthrough of UniPro 2.0 is completed. I would like to hand over it to Bruno.
Hello, everybody. I will start. So first thing, UFS 4.0 basically takes advantage of M-PHY 5 as well as UniPro 2.0. So I will not talk about bandwidth anymore because my colleagues have already done it so far, and JEDEC is really working on in close collaboration with MIPI in order to develop together the next specification. So basically UFS 4.0 was developed closely with MIPI, and the next generation is basically going down the same path. Nevertheless, we realized that we had our last webinar talking about UFS 3.0, and there has been an intermediate release in between, the 3.1. So I will talk also about a couple of features that have come since then, because I think they are very interesting for the end users. In fact, the first one is this 3.1 write booster function. Okay, I don't know how many people now in the audience are familiar with NAND flash technology, but the mainstream NAND flash technology now on the market is called the TLC, triple level cell. Means that in every cell of flash you can store up to 3 bits, basically 8 different values. But when flash was invented several years ago, you could store only 1 bit per cell, meaning 2 values. Now, what happens is that introducing this extra complexity also slows down the process of reading and writing into NAND flash, especially. This means that you have to perform a series of electrical operations in order to store your values correctly, and if you are off a little bit, basically the content of your flash is unreadable and unusable. So we came up with the idea to define some special space inside the UFS device in SLC mode. So this is TLC flash used in a single level cell mode, which offers, we say, around 3 times faster performance when writing, but this is really technology dependent. So each vendor may really have its varying mileage. And what you do is you can enable this write booster buffer, which is a special area cut out from your main array. You enable it, you write down because maybe you need to flush lots of data, and you do it with a much higher performance. And then when you don't need this higher performance, you can disable this again and live with your TLC performance if you're happy with it. And basically, there are two flavors that you can use here, which is a preserve user space, in which this buffer is dynamically changed according to how much TLC is left for the main storage, or a user space reduction, in which you basically say, okay, this is some amount of memory that I want to preserve in my SLC mode, and basically this means that the total amount of memory that the user sees is a little bit lower, because SLC, basically if you have 3 gigabytes of TLC, you will then reduce them to 1 gigabyte of SLC, because it just you can store less data. What happens is that once the data is stored in the write booster buffer in SLC mode during background operations, or when the device is in hibernate, it will be flushed to the normal storage, basically meaning that the user does not really need to take care of knowing where data is stored. The device will manage it by itself. And we also offer two modes of using this with a dedicated buffer and a shared buffer, meaning the UFS devices are comprised to up to 31 logical units, and you can decide that the write booster buffer is active only when write to a specific logical unit, or you can decide that every write to the UFS device need to be buffered, and this is the shared buffer mode. Which gives you the best performance really depends on the kind of application that you are running. And so, I mean, before choosing one or the other, or whatever the flash vendor that you choose is offering, basically you do your own simulations according to the workload. The next feature was introduced, not really in UFS 3.1, but we published an extension specification called the Host Performance Booster at the same time as UFS 3.1. This was done to solve also another issue with the inherent technology with the NAND flash. And this is the following. Basically, UFS is a managed device solution, meaning that you write to NAND flash only using your logical address, but the device controller performs a lots of background operations like called garbage collection and wear leveling, in order to make sure that the flash lives as long as possible. And also when writing to flash, you need to write one block at a time, meaning that you cannot just overwrite a couple of bytes of data. You need to transfer larger blocks. That means that invalidating one block and transferring to another place. The host never knows where the data is really stored physically. Now, in order to keep track of this, the flash device keeps logical to physical address translation, L2P table or L2P map, in its NAND flash. And this is stored in NAND flash because it needs to be kept across power cycles. Otherwise, you don't know where your data is. Now, as NAND flash densities have been increasing, this started to cause a problem, because access to NAND flash to read this L2P table is quite slow. And therefore, this L2P table is cached in an SRAM inside the device itself. Now, if you have a 1 terabyte device, the amount of SRAM that you need may go up to 2 gigabytes, but a 2 gigabyte device of SRAM, it's too big, too expensive, does not really make it as a viable solution. And if you have a cache miss, which may occur quite frequently in a larger device at this point, because you cannot cache every address in SRAM, this means that your access time will be much longer, because you're not accessing anymore from SRAM to an address, but you have to read it from flash, and this takes really lots of time. So what we thought about is we can offload the content of the L2P map to the DRAM of the host, so that the hosts have much larger quantities of L2P map available, and with some special protocol extensions that we introduced at the time, the host can now directly address the physical address of data, does not have any more to go all through the pain of a cache miss. It will be much less frequent. And again, here we offer two different modes of operation according to what the user wishes. One is called host control mode, it's on the right side, and the other one is the device control mode, and this is on the left side. In the device control mode, it's a little bit easier to explain. The UFS device, according to how the read patterns are, can identify some regions of data, and it sends a hint to the host, recommendation to say, you better cache now these addresses because they are frequently accessed in a whole region. And with a special command, the host can tell the device to transfer then the L2P map in a special memory zone for of the host memory in DRAM, and basically from that point on, the host can directly refer to the physical address locally. In the host control mode, then this is a little bit, the transactions are a little bit more, but it gives also more control to the host system, because the host may decide which regions may need a more frequent access inside the device. At this point, it may activate those regions, and again, there is a transfer of the L2P map into the host memory. Nevertheless, what happens is that in both modes, actually, some of the regions then may become, let's say, need an update, because probably there is a write into memory, therefore, or some garbage collection has happened, therefore the L2P map of some regions is not anymore valid, and you need to update this. Therefore, the device can just signal to the host that this data region is not anymore valid, and new data can be transferred there. Now, as this is an extension specification, this applies to both UFS 3.1 and 4.0, as well as every new feature that was introduced in 3.1 is also kept in 4.0, as the case of the write booster buffer. Okay, so both Ramesh and Sergio discussed about the high-speed link startup support. This was a little bit of a headache for JEDEC. We've been wishing this for a long time. Nevertheless, when we got it, we just realized, okay, now we also have to find a way that the old and new systems can work together, because backward compatibility, at least across one generation, is really important for the survival of a standard. And what we see on the market out there is that there are mixed systems, meaning maybe you have a UFS 3.1 host and you have a UFS 4.0 device, or the other way around is a little bit less common, but also exists. So we just decided, since high-speed link startup and low-speed link startup will not be able to talk to each other, so you will not be able to bring up your system with a capability exchange, we just defined a pin from the package that is a static, and if it is 0, you have a low speed link startup, and one high link speed link startup. You may use just a 0 error resistor or whatever you want to bias the spin, and basically, without changing the board design, you may be enjoying a high-speed link startup if you want, if you have it, or you can throttle down to low-speed link startup if you're forced to. And this ensures the backward compatibility between UFS 4.0 and 3.1. We introduced an advanced RPMB mode. RPMB stands for Replay Protected Memory Block. And this is a security feature of UFS. We define 4 regions of, I think, 16 megabytes each, where you can store protected data, meaning that in order to access this region, you do not only need to provide a key value, but it is also calculated with a so-called nonce, which is a value that changes each time, and is basically there is some operation between the key and the nonce. So if anybody is sniffing the bus between the host and the device, he will not be able to catch your password and access your data. On the left side, you can see how the RPMB mode has been working for all these years, and in UFS 4.0, we decided to use some extended header segment that was available in our UPIU, which is our basic transaction unit in the UFS standard. And in order to simplify, so this basically means that with less amount of transactions, you will be able to transfer the same or more data, same amount of data over more data, thus reducing the burden on the CPU and reducing the latency of access. Multiple queue support is not belonging to the UFS 4.0 device standard, but to the UFS host controller interface, which goes hand in hand with the UFS device standard, of course. Now, this is a feature that has been introduced in order to improve the performance of random accesses. So when you have lots of smaller accesses, let's say 4 kilobytes, read and write, historically, UFS had a doorbell register that you could ring and pointing to some base address, but let's say that the operations were done once at a time, and this is okay for sequential accesses. If you have to transfer some megabytes of data or several tens of kilobytes, but with small atomic accesses was a little bit of a burden, and especially as the transfer speed gets higher with higher speed gear, then the amount of time between two transactions is shorter, meaning that the host has to intervene more often, and this is not wished. So basically, we introduced some circular queues. And you can have up to 32 submission queues and 32 completion queues. If you have multiple cores in your system, these queues are core agnostic, meaning that you can have a submission queue and a completion queue referring to the same core, like in the example core 1. Example core 2, core 3, you have intercore messaging, meaning that you have, for example, 2 submission queues belonging to core 2, and the completion queue that is carrying the response from the UFS device to the host is then managed by another core. And then you may have also another situation which is called intra-core messaging, in which maybe you have 3 submission queues belonging to core 4, but core 4 also manages its own completion queue. A queue is defined by a head, a tail, and a certain number of messages, which are just normal UTRD messages, so the normal message structure that was and is still historically used in UFS. But in the case of the completion queues, a slightly different format has been introduced, but let's say it does not have to be compatible with the older standard in this case. This provides the benefit that the host software has multiple points of access to the host controller interface hardware. In order to support this, there was a small change in UFS, so it was not really strictly needed, but still improves the performance, because the UFS protocol has one feature. It's called the initiator ID. This is especially useful in systems supporting multiple cores. Basically, what you see here is that each core can have its own initiator ID field, and up to 16, as was in legacy, was okay. But then when you see that you have multiple queues and you up to 32, and then different cores, and you have multiple completion queues, you want really to be able to identify what is going where with a higher granularity than 16. So we just extended the initiator ID to 8 bits instead of 4. We had to, because of how the UPIU format was laid out, we had to go to a little bit to a trick here, and we have 1 byte for some transactions going from the host to device, and byte 8 for the transaction going from the device to the host. But this is working on the field, no problem, and basically it allows to distinguish up to 256 initiators on the UPIU level. Now, I see time is running a little bit out, so I will not go into the detail of all these other improvements that we have introduced. But on UFS 3.1, we have a notification of performance throttling in the deep sleep power mode. UFS 4.0 introduced a barrier command, out of order data, RPM B purge, I'm sorry for the typo there, read buffer, and also in order to enable newer technologies and lower power consumption, we dropped the support for 3.3 volt operation. Now the highest voltage you can connect is 2.5. And I think that this finishes my part of the presentation. So I think I'll stay on stage so to see if there are any questions coming in.
No, stay on stage, yep, and hopefully our other speakers will join us. So yes, Sergio, Ramesh, please come back to the stage. Whilst we've got you here, Bruno, perhaps we'll just go straight to a couple of questions on your presentation that came in. First one was asking a question about slide 21. It says that SLC buffer is actually SLC, or is it peer SLC?
This depends really on the implementation. So what I mean, the concept of the right buffer does not even need NAND flash behind. So we call it TLC and SLC because these are the main runways right now that we have. It is mostly PSLC, I think, in all implementation, but it does not have to be like that.
Okay, thank you. Okay, so I see all of our speakers are here, so let's take it from the top. So first one, I think, probably is during the M-PHY presentation. So maybe for you, Sergio, as far as chiplet is concerned, compared to UCIe, what does M-PHY bring?
Yes, so these are specifications for different use cases. UCIe is meant for die-to-die interconnection, so basically dies or devices that sit in the same physical package, while M-PHY is meant to be used for devices that sit on different places of the assembly board or PCB, so with the different packages and longer interconnections. So that is the key difference of these two. They are basically meant to be used in different ecosystems, and so far have different characteristics.
Okay, great. Okay, so next one. Okay, Flash is low-speed device. Does UFS make chip-to-chip connection faster? Any of you like to take that one?
Okay, I'm not really sure that I understand the context of the question. Nevertheless, the interface of Flash is getting faster. What Flash vendors do is they tie several chips in parallel to increase the speed. So when you think you're writing to one Flash chip, maybe you're writing to more Flash chips in parallel and scattering your data around. And yes, there is a strong need for from Flash device vendors to have higher interface speeds.
Okay, let's leave that at that. Next one, does UFS allow use of other transport layer, link layer, SerDes combinations other than UniPro and M-PHY?
Theoretically, yes. So it is this built in a layered mode. So UFS is agnostic let's say 99% to what's below the application layer. De facto, we are going on with UniPro and M-PHY.
Okay. Okay, next question touches on backwards compatibility, I think probably specifically related to Ramesh, to the UniPro specification, asking about why some earlier functionality was removed in v2.0. Ramesh?
Yeah, so when we say that earlier compatibility removal, it's more like, by specification wise, it has been removed basically to ensure forward progress has been much more easier in terms of introducing newer features which are required in the industry. Whereas one of the major thing that industry wanted to get away or get rid of is optical media converter, right? And optical media converter was not having any a need talking about storage solution, right? That is where that need to be dropped off. That's why the specification-wise compatibility is being maintained up to one version back. Whereas in case of actual device makers, with the consideration of custom things, they can still able to make sure the compatibility up to one version lower is possible.
Okay, thank you, Ramesh. Bruno, Sergio, anything to add on this subject of backwards compatibility?
Yes. I don't think that UFS 2.1 will be available still for a long time because flash memory vendors streamline their processes, and it will not be cost effective anymore because you just shift to the next generation and you bring everything there. So okay. Yeah, I understand the problem. It is really an issue for some vendors, and I'm sorry for this. But let's say, yeah, the situation is much more complex than this, and sometimes you have to do some sacrifices.
Okay, thank you.
When the high-speed reset mode was discussed in M-PHY work group, we had to choose one default high-speed rate to be used. And this is because whenever UniPro issues a reset, the PHY will fall back to the default rate and gear. And because in this particular application, there was no other way envisioned to have selected a different rate, it was decided that after a reset, the PHY would default to high-speed gear 1 rate A.
What is the UFS advantage over NVMe in automotive applications? Bruno, maybe that's for you.
Let's say that both are aimed at different applications, even in the domain of automotive. So the advantages of UFS are lower power consumption, really faster boot up time. Now, especially in UFS 4, thanks to the work of M-PHY and UniPro, this is getting even better. But it was already the situation since UFS 2.1. Probably it is also sometimes gets to a cost factor. UFS is traditionally cheaper than NVMe, also because of architectural considerations, where the controller lies, and so on. Then we have other situation, but that maybe like many automotive vendors prefer to have a soldered solution to a mechanical connector that can get like erosion and other connectivity problems over time because of all the mechanical stimulation, and the car is basically needs to last 10-15 years long and not a couple of years like a mobile phone. So there are different things that makes it a sweet spot. It's still right now UFS is really big in the automotive sector, and NVMe is has some other advantages on its own, but is still in a niche sometime, and in some years things may change, but we don't know yet.
Okay, thanks, Bruno. I'm conscious of the time. We've got literally 1 minute, so there's perhaps one more. I think this is again UFS related. It's about whether there are plans for UFS to meet ISO 26262 automotive applications.
This is vendor specific. So JEDEC does not take care of this. If you select a memory vendor, they will provide you automotive grade parts or not, according to their commercial policy.
Okay, page 7, the introductory part. We talked about mobile and automotive. What about client products, Windows, Chromebooks, etc.? Is this a kind of relevant market area for the solutions we've talked about?
And then there are solutions available if you browse the web for those. Exactly what is the percentage? Something someone else might be able to talk about.
Yeah.
But there are use cases growing out of standard mobile to laptop and desktop environments, automotive, and some other more specific use cases outside these more typical ones.
Okay, we're going to have to wrap it up there. Unfortunately, we've reached the hour. So thank you, presenters, for the excellent presentation today. And that's just a resources slide. So if anyone wants to find out more about any of the technical specifications discussed today, you can click on the appropriate link here, go through to the relevant webpage. Obviously, we always encourage anyone who's not already involved to get involved in MIPI, into our M-PHY UniPro working groups. Likewise, JEDEC, I'm sure would be very happy for you to join
Sure.
their group. If you are sort of struggling to find answers to your questions, then please reach out to admin@mipi.org, and we'll do our best to answer your questions or point you in the right direction. I wish everybody a good day, and hopefully we'll have a chance to present to you again in the near future. Thanks a lot.
Thank you for attending. Bye.
Thank you for attending. Goodbye.